Hi, today I will demonstrate this light microscope. This is a little bit more advanced than the one that you have seen in undergraduate school perhaps. This one can both do reflective and transmitted light, and it can do polarization and differential interference contrast, as well as lambda contrast. I will go through and show these different techniques on this microscope, and to do that we need some samples. So for the dark field imaging, I've chosen a silicon sample here, and for the polarization I have a sample that's from the lily of the valleys. This is the root we're going to study. Then I also have two microtome cut paper. So this is a paper where we have printed a silver nano ink on top, and we want to study the cross section of this print. And the first step is to do that with light microscopy. So here I have two samples to show that, and one of them I've used on this lambda contrast. What you can see here is that this microscope can both do top lighting and bottom lighting. So when you use the top lighting, you collect the reflective light of the surface. That is very useful if the sample, for example, is not transparent to light. Alright, let's put in the silicon sample now to demonstrate the dark field imaging. Here is the dark field image. We can go to a higher magnification. So here it's 100 times. The black thing in the center, that's the silicon. And what we're looking at is a cross section of it. The silver looking thing around, that's the aluminum that's been used in this process. And what we want to do in this particular sample was to study the distribution of this aluminum and see if it's completely fills the pore or if there are empty spaces like that you see in this picture. We can switch back to the bright field view. Here you see that the silicon surface become very white because now it picks up all the light that's reflected back. So this is the standard bright field image. So all things you see here on the microscope, these ones at the top for example, those are for the reflected light option. This piece you choose the differential interference contrast option with. This piece is for the dark field imaging, and here you have some color filters. On the bottom here you have the focusing knob. You raise the table up and down, the XY translation stage. So here you have the polarization filter in the bottom that you can put in like this. You can adjust the angle of the polarization with this wheel. Here you choose the aperture of the condenser. Usually you have different apertures that matches the objective. So here it says D, that's for the dark field imaging. Here it says 40, and that's used for differential interference contrast. Then you have the 40 times objective. Same thing here, 10, 20, that's for the 10 and 20 times objectives. 5, and this H is just for standard bright field imaging, so that's basically no aperture. You can adjust the position of the condenser with these two knobs down here. And with this wheel you choose the options of the Wollaston prism. And you have different settings here depending on if you do a differential interference contrast. Then you can adjust the effect of this, and you can choose the dark field option, or H, that's just the standard bright field option. The top one here is a reflector, 1, 2, 3, 4. Here you choose how the light shall be reflected inside this microscope. It is used when you use reflective light, because then the light comes from the light source over here and goes through here, down through the objective, and then it reflects back upwards again. So how to collect this light is governed by this reflector. Here you have the revolver with different objectives. You can look at the color of the rings here, and it will tell you what kind of magnification it has and if immersion oil is needed. Here, for example, white rings means 100 times, and the bottom black ring says it needs oil. I have already prepared a sample that's been ultra microtome. The sample is a paper that we cut in thin slices, and we're going to look at the cross section of that, because on top of the paper a printed silver non-ink pattern is made, and we want to study that And the first step is to do light microscopy on it. So I already made this sample beforehand, and we're going to put this in. This is the bright field image of these slices that were cut with the microtome machine. You can see three of them here. The small squares you see inside them here are the actual paper. And we're going to study the print, and the print is located here, for example, on this slice. So let's zoom in. You can see when you look at this that the width of the ink is sort of the thickness of the paper, so perhaps 80 micrometer or something. You see, now we have come to 400 in magnification, and now we start to see the height, the thickness of the ink. Let's put on some immersion oil and choose us the 1000 magnification and see what's the limits of this system is. So here you see the immersion oil. There are different refractive indexes on them, it's written on here, and you need to match that with the objective that you use. This one is 1.518. So you put a drop on this on top of the cover glass. The idea is that the drop shall fill the empty space between the objective and the glass. And that will collect more light into the objective. And here you have the ink, the black piece in the center of the image. That is the printed silver nano ink. You can also see it has some rough texture at the surface also. This is the end of light microscopy. This is sort of 1000 in magnification, and the details you see here is so. You can go a little bit further if you optimize the technique and choose a blue wavelength and sort of, but in practical this is the end. And all these views we've seen now, that is bright field imaging. You can go and see how dark field imaging will look at the same image. So we go to and study transmitted dark field. Okay, so here I put up the dark field image of transmitted light. Now you can see this is the 400 magnification scale again. Now you have the reversed case. Everything that was bright before now becomes black. So it is only the thing that is reflected in the sample that's picked up in the objective. And here you can see this small yellow stripe, that's the printed ink, of course. Now you remember that the printed ink was black before, now that is the reflecting piece here. And of course it's printed silver, so it should be reflective, right? Let's go back to the bright field image again. So here is the sample again at 100 times magnification, and this is the bright field image. You can see that there are some water drops here that's been trapped inside between the glass pieces. And you can also see some part of the slice edges here. Now we're going to switch to the interference differential contrast mode. And you know that enhances the effect when the refractive index changes in the material. If you have phase contrast, for example, then you know that different material with different refractive index will have different contrast. But in differential interference contrast, it is the change of refractive index that's enhanced and made into great contrast. So it's sort of like the derivative of the phase contrast image. So now I set up the microscope for differential interference contrast. First I change the condenser aperture so it fits the objective. Then I change this Wollaston prism on top and put it at the right section B2 here. Then I change the reflector so it goes into position 1. And then I will change the polarizer and check so that is in the right way. So I put in it with the polarizing upwards. So here you see it. This is the differential interference contrast. And the most recognizable feature of this technique is that things start to look three-dimensional. You know the small water drop I talked about? They look like small bumps now. This looks like the surface of the moon, sort of. And that feature is the one that you want. And especially if the sample is equally transparent to the light, then this method is the only technique that you actually can see some contrast. Living cells and things, if you study that look very nice in differential interference contrast. So here I have another microtome slice paper.
This paper has a top coating of plastic that will look very neat with the lambda contrast. We'll try that.
So now I switch to 200 in magnification. Now clearly you can see the printed ink, and beneath it the transparent coating layer. The purpose of that layer is when you print with regular ink, it's supposed to be transported down to the inner layer and thereby get some kind of protection to physical touch and moisture. So let's see what's happened when I put in the lambda plate now. Okay, in order to make lambda contrast, we change the polarizer on this left side and put the lambda plate upwards. That will make a colorful effect on the sample. So, because this sample is a microtome cut, it's supposed to be the same thickness everywhere in the picture. But you can also see that the lambda plate makes different colors. And that means that the traveling length of the wavelength of light when it passes through this slice is different. So if this light traveling distance is different, then you get a different color. So then you can compare it to the plastic coating layer that we used when we embedded the sample. That's the top one, that's red here. Compare that to the bottom coating layer that sort of looks purple in this image. So this is a very neat way to enhance the contrast of this light effect. By turning on the prism you can enhance or decrease this effect or the scale of it until it's completely turned off. Then we're back at the regular bright field image again.
On this side of the microscope you have a knob to focus the condenser. You can choose different lenses of the condenser. You can change the top polarization filter. If you flip this upside down you get the lambda contrast effect instead. This is a knob to select how much light goes into the binoculars and the camera, and this is just a shutter to close the camera. On the bottom here you have options to control the light source. You have the intensity of the lamp, you have the focusing of the lamp, you have an aperture of the lamp. And there are two light sources you see here. The one on top is used for the reflective light option and the one in the bottom is used for the transmitted light option. Here I have the samples of the lily of the valleys. This I will demonstrate the polarization light method on. So now we're going to check the center region of this of the core of the lily of the valley root. So here in the image you can see that the root's central core. And it's in that core the starch is located. The starch is molecules that organize themselves into crystal-like patterns. And everything that's ordered will have effect in polarization microscopy. So when we put in the polarization filter now, we will more easily see the starch. So let's do that. So here you can see that the white regions around these holes is the location of the starch. Now they are more clearly visible and you can easily distinguish which sites has the starch molecule. Okay, I think that's it. Now I demonstrated the light microscope and all the different procedures and operations you can do with it. Hope it helped you. See you.